What you just saw was a fully autonomous drone system, and today I will show you how I made it. Starting off, we have our drone game object, which contains our scripts. First, drone controller, which is responsible for movement. We define our move in direction function, which takes a direction vector and moves the drone in this direction. We will also define a helper function that allows calling it using a 2D vector. Finally, we define a function that moves the drone to a specific point. We get the direction of movement using a simple vector operation. If the magnitude of that direction vector was really small, we can say that we reached that point, so we'll return a true to indicate that. Otherwise, we will move and rotate the drone towards the direction, and we will also add a hovering function for the drone to go up and down. To control our drone manually, we first initiate our input actions, WSD for movement, and for hovering we use Q and D. Now back to our drone. We have the drone input action script, which creates an instance of the input action system we just made. During the update method, we will take the movement direction and the hovering value. Finally, we will define the events, invoke them, and subscribe to them in the drone controller. That's it, we can now move our drone. The body is working, now work on the brain. How can we detect this flag here? Let's use YOLO for this job. You collect some data, annotate it, and start training a YOLO model. But there is something odd. Classification loss is falling, recall is perfect, and yet mean average precision is 0, with no signs of improving. Welcome to the curse of tiny object detection. What is going on here? This is a casual symptom for the long tail problem. The long tail problem is when we have a class imbalance. One class is so frequent and the other is super rare. That is, if the model just focused all his effort on the most frequent class and completely ignored the less frequent one, then the overall performance of the model will still be good because the predictions from the more frequent class are overshadowing the errors from the less frequent one. You might be asking, how do we even have a class imbalance here? We literally have a single class, this flag over here. Well, YOLO always adds an extra class for background. So this is the issue, right? We just need to have more images with flags, right? Sadly, it is not that simple. If you actually look closer to our training log, you can see that it's saying we have 210 training images, where 87 of those are background. So this is actually about 40% background and 60% flags. What is going on here exactly? Your issue was looking at this as one big image, which is not what YOLO does. Behind the hood, YOLO takes the image, creates a bunch of anchors, and adds multiple boxes with different scales at each anchor. Then, it labels each one of them accordingly. And actually, most of the boxes here are labeled as background. It's just this little box over here that got a part of the flag in it. We have a hidden long tail problem here. And this actually explains the numbers here. Recall and the classification loss are doing fine because we are correctly predicting the classes of each background object, whilst the FL loss and box loss weren't improving because we aren't even trying to predict any boxes, while the mean average precision remained at 0 because if we aren't predicting any boxes, then there is no precision for the boxes predicted as they don't exist in the first place. So how do we fix this issue? One option might be to get a new dataset, but this time have the flags laid out more frequently so they cover a bigger portion of the image. Although this is the best solution, it's not always an available option, as it may require lots of preparations and permissions to run another survey. Let's try to come up with a more creative solution. Another option might be to use a synthetic dataset generation, an augmentation pipeline that takes our images, sees where the flag is, duplicates it with random orientation and scale. This option is actually quite good and fast to set up. Its only issue is that it can create some unrealistic cases which will break cues for our model. For example, you can see here that we have some flags placed on top of cars. This is extremely unrealistic and will confuse the model. Coding this is really straightforward. We initialize our transformer class with the number of objects we want to paste and the probability of this augmentation occurring. We extract the image and the annotated boxes. For each new object we're supposed to paste, we get a random object from the current image. Then we paste it, getting the coordinates of the new box, and add it to our array of newly added objects. Finally, apply our changes to this training instance. We make a custom YOLO dataset that applies the transformation we just created, and this is how an image from our dataset looks like. Now we create a custom trainer that uses our dataset. Finally, we train a YOLO model using this trainer. After just 20 epochs of training, we reached an almost perfect mean average precision value. I have this other video where I explain the code you are seeing here in far more details, so make sure to watch it out if you are trying to build something like this yourself. Looking at this hidden long tail problem, we might realize something important about AI. In web development or standard software engineering, we often treat libraries as black boxes. You don't need to understand how it works to use it. But AI field is really different. The bug we found here, it wasn't syntax error. It wasn't a logical error. The code actually runs perfect. The error was purely mathematical based on the hidden implementation of YOLO. That's why we study statistics and calculus and read research papers. It's not because we want to write the algorithm itself from scratch, but because the only debugger you have here is your mind. Before coding the AI server, I will first export our model as OpenVino. OpenVino is just a model optimizer for neural networks to run faster on CPU. Here is our model performance without OpenVino. Runs at about 10 FPS per second. And here is with OpenVino. It had a slow start because it was loading some parameters and stuff into memory. But once it was done, it was running at 30 frames per second. To fix this slow start issue, we can make a dummy call first to initiate our model parameters so that it can run with the best performance directly. This process is known as JIT or just-in-time loader. Anyhow, let's move our model files to the AI server. Now, starting off, we will be using Fast API for this, so importing the libraries, setting up the app, and loading up the model utilizing the just-in-time loader we talked about earlier. Now, back here, we'll include our API's main router, which is something we defined in this other file as an API router. An API router is just a handler for the possible routes a client may visit. For example, we can handle a GET request at the home directory, returning some info about our API. We will also make a route where the user can upload an image. Then, we'll use our model to detect where the flags are, returning their positions and the confidence of this prediction. We can use Postman to interact with the API to ensure that everything is working correctly. The results are looking really good. We're now ready to integrate it into the drone. In our drone, we have this flag detector script, which is responsible for detecting flags, obviously. In Unity, we use render texture to get the image the camera is seeing. We initialize it here, then we use it to extract the image, convert it to a texture 2D, and send it to the server. We send it through a sample request containing our image, just as we did in Postman. Handle any possible errors, and finally invoke an event with the response found, so anyone can be notified when we see a flag. At this point, we have the drone body functioning and we have the eyes functioning. What we are missing now is moving the drone according to what our eyes are seeing. If we saw a flag, go towards it. Otherwise, keep searching. Now, the question is, how can we decide our actions? One way is by doing a long list of if-else statements. If we didn't find the flag, keep searching. If the flag was found, go there. If we reach it there, drop the payload. But notice how this if statement will still run even if we are on top of the flag. We need to add a condition here to ensure it won't run if we are already on top of the flag. Our code is quickly becoming spaghetti. And we are only having 3 states. What if we added more? This will be really painful to manage. A clear structure is called state diagram or finite state machine. It indicates that at any given moment, our drone is at one and only one state. Like initially, we start at the surging stage. When we find a flag, we transition to a different state to start going to the flag. When we go to the flag, transition to a state to drop the package. And if we are done dropping the package, transition to a state to bring us home. Now, what if we were at the searching stage and we didn't find anything? We'll transition to our terminal state, which brings the drone back home. As you can see, handling cases here is much easier. We just need to decide what state sends to what and when. No more if conditions, no more spaghetti code. This structure is way cleaner and more predictable and easier to debug. Coding this was actually really straightforward. We just define our states here and toggle through them during our update function. We initially start in the searching state. The searching pattern itself is defined here as a Lauenmauer pattern, where the distance between points is defined dynamically according to the area our camera can cover. And here in our search function, we traverse through this grid in order, and if we run out of points, we return the drone to its launching position. Now we need to handle if we find a flag while searching. We do this by first subscribing to the event fired when we find a flag, and handle it by first ensuring that we actually detected something, and then look over all the predictions, getting the normalized pixel positions, denormalizing it, and now we end up with the flag position in 2D space relative to the camera pixels. We convert it to be something relative to the world position in 3D space. We do this through a simple raycasting algorithm, seeing where it hit, adding some noise to simulate real-life scenarios, and just returning the position. Then, we assign this position as the target point we want to go to. Finally, we change the drone state from searching to go to flag. And now, in our next update function, we will run this go to flag function, which just moves the drone to the target point. And if we reach it there, we'll change our state to hover with drop. So in the next cycle, we'll be here, which will just run this function, which will wait for a few seconds to stabilize the drone, then let the package fall. Finally, set our state to the terminal state to terminate the mission. Alright, let's see how this all looks like. That wasn't bad, that was giga bad. Maybe we're just unlucky. Let's try again. No. Nope. Yeah, there's clearly something wrong with our system. Let's have a closer look at our model predictions. It is detecting nothing here, which is good. And here is an issue. 23% confidence that this is a flag. We call this a false positive. The model falsely said that this belongs to our positive class, the flags. If we continue scrolling, another false positive here, and lots of them here. This frame contains the actual flag, and you can see that the model was able to find it with 94% confidence. We call this a true positive, as the model classified this as a positive class, which is true. We need to somehow eliminate all the false positives we have, and only get true positives. You may think that changing our confidence threshold will be our solution. Anything above 90% will be a flag, and anything below won't be a flag. Sadly, it's not this simple. If we had a look at our training logs, we can see this really important metric called box precision. Precision is a metric that evaluates how well our model is doing in its own predictions, meaning that if we have 10 objects lying around and the model only predicted 5 boxes, precision is the accuracy of those 5 predictions only. 4 out of 5 here are correct. Our training logs shows that we have almost 97% precision. Although this is a really good number, you must remember that our model runs at 30 frames per second. So each 10 seconds we will analyze 300 frames, and out of those 300 frames we will have 9 false positives. Each 10 seconds, our model will see 9 objects falsely classified as an actual flag with a high confidence. Our drone is guaranteed to waste the payload, so improving the model or training it more won't solve our issue. Let's think about the solution in a more statistical manner. The probability of a false positive being detected once is 3%, and the probability of the same thing being classified twice as a false positive is 3% multiplied by 3%. Almost zero. Now, for a true positive, the probability of detecting something once is 97%, and the probability of the same thing being classified twice as a true positive is 97% multiplied by 97%, which is 94%. I hope you got the idea of our solution. We will have an evidence accumulation system, where classifying something as a flag once is not enough. We need it to be classified multiple times as a flag to ensure that it's actually a flag and not a false positive. Now, in our code, we'll update the on-flag detection behavior. Instead of adding whatever was detected directly, we run our evidence accumulation system. First, we neglect anything below 60% confidence, as this stuff are mostly just noise. Then, after getting our target, we add it to our targets list, which initially checks if our target already exists in our targets list by comparing the distance between our target and all the other targets in memory. If it exists, then we run this function, which just increases the confirmation score of this target. It also updates the position using an exponential moving average filter to cancel out any noise due to sensors. Back here, we compare our target to the archive targets as well. An archive target is a target that was already confirmed as a flag, and we are keeping track of them so the drone won't visit a flag that was already visited. Finally, if it wasn't found in both, we add it as a new target. Back here, if anything was confirmed as an actual target, we first archive it, then set it as our dropping target, and change our drone state from searching to going to that flag. And that's all. I'm planning on releasing other videos similar to this one, like this autonomous car you are seeing here, or you can directly give me new ideas in the comments below, so make sure to subscribe to not miss it out.